It's this idea, what if the distance light travels isn't fixed? Like, could it get shorter if the space it's moving through is, moving really fast?
Wow. Okay, that's not a trivial question. That shows some really sophisticated intuition, actually.
Right. It feels like it goes right to the heart of, well, modern physics.
It absolutely does. Because that query,
Mhm.
it directly challenges our everyday classical ideas about space and time being absolute. It points straight towards Einstein's discovery that they're really observer-dependent measurements.
Okay, so that's our mission for this deep dive, using the source material, relativity of light, confined systems, and space-time dynamics. First, we want to explore that core idea you raised. We'll get into exactly how and why the space available for light is relative.
Precisely. And second, we need to tackle a common stumbling block. People often try to imagine things from the perspective of light, from a photon's point of view.
Ah, right. I've heard that's problematic.
It's fundamentally impossible, physically speaking. So we'll explain why and introduce a more rigorous way to think about it, a physically sound model that actually works.
Sounds good. So how do we get there? What's the roadmap?
Well, we have to start with the foundations. Einstein's two famous postulates, they're the bedrock.
The rules of the game, basically.
Exactly. From there, we'll see what those rules force us to accept about space-time, and then we'll bring in this concept of a box of light.
A box of light. Okay, intriguing.
It's a way to think about confined light, an electromagnetic system that does have a valid perspective, a reference frame, unlike a lone photon. And it behaves kind of like an object with mass. This will be key.
All right, let's rewind then, back to 1905. Einstein, the patent office.
Yep, that's the place. His paper on the electrodynamics of moving bodies, it just turned physics upside down with two, well, deceptively simple-sounding ideas.
Deceptively simple is right. So postulate number one.
That's the principle of relativity. It basically says the laws of physics are the same for everyone who isn't accelerating. So if you're just drifting along at a constant speed, your experiments will give the same results as someone standing still.
No special rest frame in the universe.
Exactly. It killed the whole idea of the luminiferous ether that invisible jello people thought light waves needed to wave through. Einstein just said, nope, don't need it. There's no absolute stillness you can measure yourself against.
Okay, that's big, but maybe not totally mind-blowing yet. But the second one, that's the one that always gets me.
The constancy of the speed of light.
It says the speed of light in a vacuum sea is the same for everyone, no matter how fast the source of the light is moving or how fast you are moving.
And that just flies in the face of common sense, right? Yeah.
Totally. If I throw a baseball forward on a moving train, its speed adds to the train's speed relative to the ground. Simple.
Right. But light doesn't play by those rules. Light from a speeding car's headlights travels at sea. Light from a stationary lighthouse travels at sea. Someone chasing the light beam still measures it moving away at sea. Someone running away from it measures it catching up at sea. It's invariant.
And this wasn't just a wild guess, was it? There was experimental backing.
Oh, absolutely. The Michelson-Morley experiment in 1887 was crucial. They were trying to find the ether, trying to detect the Earth's motion through it by looking for tiny differences in the speed of light in different directions.
And they found nothing.
Precisely. A null result.
Yeah.
Which was baffling classically, but perfectly consistent with Einstein's second postulate. It was sort of the key experimental piece, suggesting light speed was constant.
So you put these two postulates together, universal laws, constant light speed, and classical physics just breaks.
It creates an unavoidable logical collision. If Maxwell's equations describing light are true laws of physics, postulate 1, and they predict a specific speed c, then that speed must be constant for everyone, postulate 2.
Which means something else has to give. Our ideas about space and time.
Exactly. We're forced to abandon absolute space and absolute time. They can't be fixed, universal backgrounds anymore. They have to be flexible, relative, part of a single entity, space-time.
So it's not just a neat theory, it's where the experimental evidence leads us.
Right. We're shifting from what seems obvious about space and time to building our understanding on what's experimentally proven about light.
And the first major domino to fall, the really big consequence, is this idea of simultaneity being relative.
Yes, the relativity of simultaneity.
Right.
It's maybe the most fundamental consequence and the hardest to wrap your head around initially. It means events that are simultaneous for me might not be simultaneous for you if we're moving relative to each other.
Okay, hang on. How does that even work? My now isn't your now.
It sounds impossible, I know. The classic thought experiment helps the train and lightning bolts.
Ah, yes, I remember this one. Go on.
Okay. Imagine you're standing on a station platform, right in the middle. A very fast train speeds past, and someone is sitting right in the middle of that train carriage.
Got it. 2 observers, 1 station, 1 train.
Right. Now, just as the midpoint of the train passes you, lightning strikes the track simultaneously at 2 points, one way ahead on the platform, one way behind, equidistant from you.
Okay. Equidistant from me on the platform.
So, standing there, the light from both flashes travels the same distance to reach your eyes. Since light speed is constant, they arrive at the exact same moment.
Makes sense. I see them together. I conclude the strikes were simultaneous.
Correct. But now, think about the person on the train. At the instant the lightning strikes, they are also midway between those 2 points on the track.
Uh-huh.
But the train is moving forward very fast. So in the tiny fraction of a second it takes the light to travel, that person moves towards where the front lightning strike happened and away from where the rear one happened.
Okay. The distances the light covers to reach them are different.
Exactly. Even though the speed of light is still c, for them that's postulate 2, the light from the front strike has less ground to cover to reach their eyes. The light from the rear strike has more.
So the front flash reaches them first.
Yes. They see the front flash, then a moment later they see the rear flash. So, based on their own valid observations, what can they conclude?
Well, they'd have to say the front strike happened before the rear strike. They weren't simultaneous for them.
Precisely. And neither observer is wrong. Simultaneity itself is relative. There's no universal now across different frames of motion.
Yeah, that's a head spinner every time. It just completely undermines our basic intuition about time.
It does. And this relativity of simultaneity is the root from which other effects, like time dilation and length contraction, naturally follow.
Time dilation where clocks tick slower for moving observers relative to stationary ones.
Yes. Though it's more precise to say an observer measures a moving clock as ticking slower than their own clock. The time measured in the frame where the events are co-located, the proper time, is always the shortest. Any observer moving relative to that frame measures a longer time interval.
And length contraction is related?
Also directly related. Objects appear shorter in the direction of their motion when viewed by an observer they are moving relative to.
Okay, so this brings us back to the listener's question about the distance light travels and that issue with the photon's perspective.
Right. So a photon travels at c. If it had a reference frame, it would be at rest in that frame. But light can never be at rest. Its speed is always c. That's the contradiction. So a photon can't have a valid frame of reference from which to observe the universe. Time wouldn't pass. Distances in the direction of travel would contract to zero. It breaks the physics.
So asking what does the photon see is just not a valid question.
Exactly. But this is where the box of light comes in. Imagine we trap that photon or just some light energy between two perfect mirrors.
Okay, like a little cavity filled with light.
Yeah. Now, that system, the box plus the bouncing light inside, does have a rest frame. If the box is stationary relative to you, it has a certain mass energy, and it exists in space and time quite normally. You can sit still relative to the box.
Right. It's a well-defined object, unlike a free photon.
Precisely. And now we can ask, what happens when this box moves at high speed relative to you? This lets us rigorously address the listener's intuition about the relativity of distance for light.
How so? Let's visualize it. Box is sitting still. Photon bounces straight across, say, vertically. Easy.
Okay, now imagine that box is zooming past you horizontally at like 80% of the speed of light.
Okay, whizzing by.
From your perspective, watching it go by, that photon inside isn't just moving vertically anymore, is it?
No. It's also moving horizontally along with the box, so its path looks diagonal.
Exactly. A longer diagonal path from your point of view to get from the bottom mirror to the top mirror.
Ah, I see where this is going. The speed of light has to be constant c for me, too.
It must be c. But the photon is traveling a longer diagonal path in the same amount of time, as measured by a clock inside the box. How is that possible?
The only way is if the box itself squishes, contracts in the direction it's moving.
Bingo. Length contraction. From your perspective, the box must be shorter in the direction of motion for the light speed to remain constant c over that diagonal path. The distance available for the light, the spatial extent of the box, is relative. It's shorter for you, the outside observer, than for someone notionally riding along with the box.
So the listener's intuition was spot on. The distance, or the spatial extent, is relative for a confined light system. The box model proves it rigorously.
It does. It provides a physically sound way to analyze the system, confirming the core idea without resorting to the impossible photon perspective.
Okay, let's try and summarize the key takeaways from this deep dive then. It really all kicked off from that incredibly insightful listener question.
It did. And it led us right back to Einstein's two foundational postulates for special relativity.
First, the principle of relativity. Laws of physics are the same for all non-accelerating observers. No absolute rest, no ether needed.
Uh-huh. And second, the game changer. The constancy of the speed of light. Always see for everyone, regardless of motion, backed up by experiments like Michelson-Morley.
And putting those two together just forces this radical rethink.
Absolutely. It means ditching absolute space and absolute time and embracing the idea of a unified relative space-time.
The key consequence being the relativity of simultaneity illustrated by that train thought experiment. What's now for me isn't necessarily now for you if we're moving differently.
Which then leads directly to observable effects like time dilation moving clocks run slow relative to stationary ones, and length contraction moving objects shrink in their direction of motion.
And finally, we clarified that conceptual point.
Hmm.
You can't use a photon's perspective, but the box of light model does work.
Right. That confined system has a valid reference frame, acts like a massive object, and beautifully demonstrates how the spatial extent, the distance available to the light within it, is indeed relative, confirming that initial intuition.
So wrapping up, here's a final thought to chew on. Our everyday world feels so strongly like it has absolute space and absolute time. We rely on it.
Completely. Our intuition is built on it.
So imagine if we could somehow truly internalize the reality of relative simultaneity. If we could feel it, experience it in our daily lives. How different would our perception of the universe, or even just our interactions with each other, be? What basic assumptions would we just have to throw out?